Welcome to the 5th chapter on dynamical systems and dynamic axioms in the Logical Foundations of Cyberphysical Systems textbook. What we're learning today is of the most fundamental importance for cyberphysical systems. We will learn how to logically characterize the dynamics of hybrid programs in differential Deming logic, which will lead us to a way of understanding compositional reasoning principles that capture how the truth of a property of a more complex hybrid program relates to the truth of corresponding properties of simpler program fragments. This leads us to discover dynamic axioms for dynamical systems, so reasoning principles that worry about the behavior of dynamical systems, which is of course spot on for understanding the hybrid systems models of cyberphysical systems. This chapter will allow us to turn the specification logic, DL, into a verification logic for cyberphysical systems, laying the pivotal foundation for all dynamical aspects of differential Deming logic and its hybrid programs. In particular, in the previous chapter, we've seen how useful and crucial CPS contracts are for cyberphysical systems, but that their use goes way beyond dynamic testing, because when we just merely evaluate contracts at runtime of a CPS, then we've got very little flexibility left when one of those contracts actually fails. Because when a contract fails, that indicates that some safety conditions that we expected to be true at that moment no longer actually is true. In other words, contracts really shine when they're proved as opposed to just being dynamically checked at runtime. So what we will learn today on the modeling and control side is how analytically as well as semantically cyber and physics interact. So not just on the semantical side, where we will worry about how the meaning of a discrete computation relates to the meaning of a continuous computation and how they interact, but also at the level of our analytic reasoning about them, will we be able to relate them. On the computational thinking side, we're developing the very fundamental rigorous reasoning principles for CPS models, which are absolutely critical to getting CPSs right because, well, CPS designs can be flawed for very subtle reasons. And if we are not sufficiently rigorous in our understanding of them, it can often be quite impossible to spot any flaws in it, let alone say for sure why a design is no longer faulty. And that will enable us to lift differential Deming logic from specification purposes, so saying what we expect, to a verification language, so justifying why things are true. On the CPS skills side, our axiomatic understanding will also give us a deeper understanding of the semantical role of CPS models, because we will relate the semantics to reasoning principles and ultimately align them in perfect unison, which will also enable us from this axiomatic perspective to develop a better intuition for the operational effects of CPSs. Indeed, our ability to conduct proofs about hybrid systems will go via understanding their effects of the hybrid program operators very well. And this illustrates part of a more general phenomenon that proof and effect, or proof and meaning, are very intimately linked. Indeed, truly understanding effect is ultimately the same as understanding how to prove properties of that effect. And indeed, you also have to first truly understand the effect in order to ever have a chance to prove properties of that effect. So what we will see today for the first time is a third leg of the logical trinity. The syntactic part that we've seen simply defines the notation that we're using, so what problems are we allowed to even write down and ask ourselves. But that in and of itself are just a bunch of mathematical symbols. Really, the semantics is the second part, which defines what carries actual meaning. For example, what real or mathematical objects does the admittedly quite arbitrary syntax stand for? Well, the syntax isn't that arbitrary because we designed it to carefully support your intuition, but only after we give mathematical meaning to the syntactic operators do they actually talk about something in reality. Now, implementing the syntax in a computer, that's real easy, just type down the characters. But implementing the semantics in a computer is much harder because it's not clear how you implement a real number with all its infinite precision and the finite compounds of a computer. But that's where they get linked. In the axiomatics, these are syntactic reasoning principles that internalize semantic relations between syntactic objects in syntactic ways. So these are universal syntactic transformations that we understand once and that enable us to make syntactic changes to our syntactic expressions in ways that are once and for all linked to have a direct semantic counterpart. For example, how does the semantics of A relate to the semantics of A and B syntactically? Well, it does so because we know that if A is true, is A and B true as well? No, it's not. But if A and B is true, then A itself is very much true. Indeed, if we know that both A is true and we know that B is true, then of course A and B itself has to be true as well. So there's syntactic relations between the formulas A, the formula B, and the formula A and B that have a semantical underpinning. And we need to make exactly the same thing work out for the logical operators. Which is where we will be using our logical guiding principle of compositionality. Reasoning about cyber-physical systems, well, that may be hard, but since every CPS is modeled by a hybrid program, well, later in the third part of this textbook, we will see that these can also be hybrid games and so on, but never mind that for now. For now, we're equating cyber-physical systems with hybrid systems, and thus the hybrid program renditions. So every CPS is modeled by a hybrid program, and all hybrid programs are combinations of simpler hybrid programs, by a program operator such as the choice, the sequential composition, or the nondeterministic repetition. All CPSs can be analyzed, no matter how big, if we only identify one suitable analysis technique for each of the operators. If we know how to handle choice, and we know how to handle sequential composition, and we know how to handle repetition, then no matter how big the CPS is, it's just a long chain of individual reasoning about the individual pieces of the program. Just like a proof of A and B is just a combination of a proof of A together with a proof of B. And this is where we will ultimately link the proof and effect of all the operators by truly understanding that the effect is really the same as understanding how we can prove properties about that. Let's first remind ourselves about the semantics of hybrid programs, because if we're ever able to develop reasoning principles for them, they have to come through our understanding of their effects. The meaning and effect of an assignment is that it takes us from an old state omega to a new state nu in no time passing, where the old and the new state agree on all the variables except the variable x that's changing, and on the variable x that is changing, the new state has a value that equals the value of the right-hand side term e in the old state. So evaluate the right-hand side, put it in the variable x, and store that in the state nu. The meaning of a differential equation is that it also takes us from an old state omega to a new state nu, but all of a sudden there's lots of those new states. Well, those states that we can get to from the initial state omega to the new state nu by following the differential equation at every moment in time, and also residing within the evolution domain constraint for every moment in time. The meaning and effect of a test is that we can stay in the current state if in the current state the logical formula that we're testing is true, Well, we cannot make any transition at all and not even stay in the current state if the current state does not satisfy the logical formula Q. In other words, we stay in place, but only if we pass the test. The meaning and effect of a non-deterministic choice is that we can transition from the old state omega to a new state nu1 with any of the behaviors that the alpha subprogram does have, because those are the behaviors that the alpha choice beta program will have as well. But also that any new state nu2 that we can go to by running the beta subprogram from the initial state omega is also reachable by running the alpha choice beta program, because the alpha choice beta program precisely has that choice. It has a choice to run like alpha or to run like beta. For example, these kinds of choices, blue trace or red trace, and either of those final states are then reachable. The meaning and effect of a sequential composition is that a new state nu is reachable from the initial state omega. Whenever from that old state omega we can go to an intermediate state nu by running the first half alpha and then running the second part beta to the new state nu. So for example, follow continuously for some time and then jump. The meaning and effect of a non-deterministic repetition is that we can go from an old state omega to a new state nu by running through intermediate states omega 1, omega 2, and so on, that we can get to by running alpha from the old state omega to the first intermediate state omega 1, then running alpha again, and then running alpha again, and then running alpha again, all the way until we're at the new state nu. But the point is that the semantics for each of those operators is perfectly compositional. The meaning of each and every one of them is just a simple function of the meaning of the pieces. And that is what we will be using to exploit in our reasoning and analysis principles as well, by developing compositional proof principles. So proof principles that also will tell us that an analysis of the big thing is a combination of analysis of the individual pieces. To have a concrete question in mind, let's remind ourselves about quantum, the acrophobic bouncing ball, which had the question whether under some initial conditions all behaviors of repetitions of the bouncing ball model are such that we're above ground and below initial height. Now, just to make our analysis easier, let's just simply delete the repetition star like so, which of course grotesquely changes the behavior of the bouncing ball. All of a sudden it can only follow through a single bounce, so the bouncing ball can no longer bounce further. But the first question we have in proving this logical formula is not so much what we do with the assumptions, because I guess we can just keep them, but how we take the dynamics of the system apart, which starts with a sequential composition operator in a box. So how can we prove that first ODE, then discrete dynamics is safe? Or more generally, how can we prove that first running one program and then running another program makes the behavior safe? In order to understand this, let's understand intermediate conditions for cyber-physical systems. So in general, the shape of the question we have at the moment is that starting in some initial state where A is true, we always want to go to final states where B holds true when we first run alpha and then run beta, which, for example, if we ask in this state, is the formula all runs of alpha, semicolon, beta are safe true here? Then what happens is that we follow alpha in any of its possible ways to intermediate states, of which there could be multiple ones. And in each and every one of those states, do we then follow beta to possibly again a number of final states, nu1, nu2, nu3, nu4, and so on, nu_n. And in each of every one of those states, does the post-condition B have to be true? Now, can we possibly prove that indeed, whenever the initial state satisfies A, then all of those final states satisfy B by inspecting the parts and bits and pieces of this program? Well, I guess for this pile of states, do we have to show something? Namely, we will have to show that all of these states will take us into B states by running in the beta program. But what are all of those states? So what we can do is identify an intermediate condition E that all of these states have in common, and then show first that from the initial state omega, all alpha behavior will lead us into states that are inside the set of states where the intermediate condition E is true, and then prove that whenever you start in this intermediate condition E, all the beta behaviors are safe. Like so. We prove that in the initial states, all alpha behaviors will get us into intermediate region, and anywhere in the intermediate region will all beta behaviors get us into safe states. This intermediate condition, that is summarizing in some logical way what all of these states have in common, of course, could also be true of other states that aren't even reachable from the initial state omega. But that's correct regardless, right? If we also for those other states prove that all the states in E, including the ones we can go to from alpha, satisfy that after running beta, the safety condition B is true, then we've also shown that for the ones where we need to know this. So of course, the intermediate condition can sometimes be an imprecise over-approximation of all the states that are really reachable by running alpha. And now all we need to do is find this intermediate condition E. That could be a bit of work. So in our bouncing ball running example, we will split it into the question whether always after running the differential equation some intermediate condition E is true. This summarizes everything that ever could have happened after the ODE. And from this intermediate condition E is all this behavior of the discrete control preserving safety. So we're above the ground and below the initial height. In fact, the latter part sounds like it would be very easy to make sure, because for that intermediate condition, all we need to know is that the position itself is between 0 and the initial height h, because the discrete dynamics doesn't change anything. But you can think about whether that will ultimately work in the long run. So the next question down the road is then, well, but how do we prove properties of choices as we have here? The question will also be how do we prove properties of differential equations, but just for complexity reasons, I suggest we stash that for a moment. How do we prove properties of a choice? Well, the behavior for non-deterministic choice is that it includes all the alpha behavior together with all the beta behavior. And if in some initial state omega, we want to make sure that all of the behaviors of the alpha choice beta program take us to safe states, that means no matter which way our program runs, we need to be going into a state where P is true. Well, but where are all those states? These are all the states we could go to by running alpha. They all need to satisfy the safety condition P. And all the states we can go to by running beta. These all need to satisfy the safety condition P, because alpha choice beta cannot run anything other than what alpha can run or what beta can run, even if those could possibly reach many possible states. So let's unfold the semantics. In this state omega is the logical formula all runs of alpha choice beta satisfy P true. If the postcondition P is true in all new states that we can go to from the old state omega to the new state nu by running the non-deterministic choice alpha choice beta. And what are the states reachable by running the alpha choice beta program? Well, that's the reachability relation of the alpha program union the reachability relation of the beta program. That means the new state nu has to satisfy the postcondition P for all new states nu that we can go to from the old state omega by running alpha. That's all of this behavior here. But also that the new state nu needs to satisfy the postcondition P for all new states nu we can go to from the old state omega by running the beta behavior. All of these behaviors need to be safe, and all of those behaviors need to be safe. But that's just another way of saying that in the old state omega, do we need to have the formula be true that says all of alpha's behavior are safe, all of these here, and independently all beta behavior is safe, that one. And that of course means that the formula alpha choice beta all of these behaviors are safe is true if and only if all alpha behaviors are safe and all beta behaviors are safe. In other words, this formula is true in that state if and only if that one and that one are both true, which means in this particular state omega that we currently talked about, it is apparently the case that the two are equivalent. So all alpha choice beta runs are safe if and only if all alpha runs are safe, and independently all beta runs are safe. But wait a second, the state omega didn't play a very important role in our argument. It was just any arbitrary state. In other words, what we've just shown is that this equivalence holds true for all states omega. And what we've just shown with the entire argument is that the logical formula that says all behavior of a program that has a choice between alpha or beta are safe, if and only if all the alpha behaviors are safe, and independently all the beta behaviors are safe, that this conjunction and this single formula are equivalent because one of them is true in any state if and only if the other one is true. And it wasn't important what alpha, beta, or p were. In other words, what we've just identified is an equivalence that is a sound axiom, meaning all of the instances for alpha, beta, p that you could possibly have to think of are all valid differential logic formulas. In other words, from now on, we can adopt it as a reasoning principle that this formula is equivalent to that conjunction. In particular, that means whenever we find a formula of this shape, we can equivalently replace it by a formula of that shape, and vice versa as well. That seems like a powerful principle, because what we just did is we decomposed the question whether all behavior of a system that has a choice is safe into simpler sub-questions whether all of the behavior of alpha is safe, and independently whether all behavior of beta is safe. Well, admittedly, there's more of these sub-questions, but individually each of them is easier than that question because it has one less hybrid program operator around. This equivalence is a very powerful reasoning principle, an axiom for a dynamical system. Let's try to see if we can develop more of them, because if we just find out for each of the operators of a hybrid program how we can equivalently rephrase their safety properties, we should be pretty much able to prove the bouncing ball, but not just the bouncing ball, any other hybrid system as well. Well, our program could be an assignment program, and thinking back of the bouncing ball, it will be assigning to velocities, for example. So we will have the question, how can we show that always after running an assignment that puts the value of term e into variable x is a formula p of x true? That means in the new state new, remember for assignments there's actually only one, is the formula p of x true. In other words, p is true of x in the new state new whenever in the old state p is already true of the new value e that it's going to get any minute from now. This equivalence characterizes what we need to do with assignments. What do we do with the differential equation? Somehow like that. We would very much like to equivalently rephrase that p of x is true always after following a differential equation in different, easier ways. What are the new states new that the differential equation could go to in which p of x needs to be true? Well, unfortunately, these could be many, many, many states because differential equations can be followed for different amounts of time. But if we have a solution of a differential equation, let's call it y of time t, then if we jump over to the new state new by the discrete assignment that puts into the variable x the value that the solution y has at time t, then if we jump over to the state p has to be true of x. In other words, this formula and that formula are equivalent, but not quite yet, because of course we could follow the differential equation for any amount of time, which means the discrete jump also we have to pursue after any amount of time, which is what quantifiers were invented for. For all times greater or equal 0, is it true that if we do a discrete jump to change the variable x to have the value that the solution y has at time t, and if we can then make sure that p is true of x after all of those jumps, then of course we've also shown that after all of the behavior of differential equation, the property p of x will be true. Of course, in order to be able to use this equivalence axiom, we had better make sure we actually have a solution of a differential equation. In the second part of this textbook, we will look much closer at what we can do for differential equations where we don't know a solution, or differential equations that simply don't have a solution that we can write down in closed form at all. What happens for a differential equation with an evolution domain constraint, Q of x? So always after following x prime equals f of x within Q of x is P true of x. Well, it should be something like that, right? It should be for all times after we put the solution y at time t and assign this to the variable x, then P is true of x. But hold on a minute, what do we do with the evolution domain constraint? Well, the evolution domain constraint is assumed to be true for the entire duration up until time t, which is what we use another quantifier for, and an implication that says for all times t, if for all intermediate times s between time 0 and the new time t, if q, the evolution domain constraint, is true of the solution y at this intermediate time s, and that was for all of these times s, then if we change the variable x to have the value that the solution y has at the last point in time t, then P of x has to be true at the state we then reach. In particular, you notice how this axiom makes the effect of evolution domain constraint more explicit. It's one example how we see that by writing down axioms we understand the semantics of these operators better. Now that takes care of almost all of the atomic operators in hybrid programs except for tests. So how do we prove that always after running the test to check that Q is true, always afterwards is P true? Well, how could P ever be true after running a test? Well, the tests don't really change states, remember, they just stutter and stay in the exact same space. That I guess means the only chance we've got is to prove that P is true right now. But now we've not actually taken the dynamics of the test program into account. Of course, if we prove that the postcondition P is true, then it's also true after we run a test, because tests don't change states, remember? But do we even have to prove that the postcondition P is true? No, we don't always, because we only have to prove that P is true after running the test if the test even passes, because the entire program cannot execute if Q is not true in the current state. Look, remember the semantics. So in other words, we only have to show that P is true under the assumption that Q is true, which means we only have to prove the implication that if Q is true, so the test passes, then we need to make sure that our present state already satisfies the postcondition. If the test doesn't pass, then no statement is made by the universal modality that says all the behavior of a program, and in this particular case just can't do anything at all. Afterwards P is true if there is no afterwards, if the test fails. In other words, this logical formula, always after running a test is P true, is exactly equivalent to the implication that the test, which is assumed to pass, implies the postcondition. These equivalence axioms now take care of all of the dynamical systems operators of hybrid programs that are atomic, so have no smaller hybrid program pieces. But notice something that's very useful about these dynamical axioms for dynamical systems. Each and every one of them is an equivalent, so we can equivalently rephrase the left-hand side to the right-hand side, or vice versa. And this was not yet the case when we're looking at intermediate conditions for sequential compositions. So maybe we can do better, actually. What we used to say is Tony Hoare's rule, rendered in dynamic logic, that says if we start in A, then all behaviors of alpha, semicolon, beta take us to states where B is true. In order to show that, we dream up intermediate condition E and show that if the initial condition is true, then all alpha behaviors take us to states where the intermediate condition E is true. And independently, if the intermediate condition E is true, then all beta behavior take us to the safe states. But we had to dream up this E, and it was a bit awkward because it could apply to more states. So let's worry about how we can shrink this intermediate condition to just the set of states that we actually need. Well, what are the states that we need? Thinking forward turned out to be a bit hard here, but thinking backward turns out to be helpful, because in all of these states, do we have to make sure that all the beta behavior is safe? So in fact, would that be a brilliant intermediate condition, E? Let's try that. Let's use all beta behaviors are safe for the intermediate condition, and that gives us the question whether the initial condition implies that after always running alpha, it is the case that always after running beta, we're safe. And it gives us the question whether the intermediate condition implies that all beta behaviors are safe. Well, but that is trivially the case because every formula implies itself. In other words, it is much more helpful to understand sequential compositions in a dynamical system's axiomatic way by saying what sequential compositions can do is go from an old state omega to a new state nu by running through any intermediate state after following alpha and then continuing on with the behaviors of the beta program. And that means after all behaviors of first alpha then beta, are we safe over here? For that we need to make sure that in the intermediate state all the beta behaviors are safe. Remember, there could be multiple behaviors. And what are those intermediate states? Well, there could be multiple intermediate states, but what we need to make sure in the beginning is that all the alpha behaviors such that all the states we get to satisfy that all beta behaviors are safe, and that precisely is what we capture as a dynamical systems axiom that says always after first running alpha and then beta are we safe, if and only if it is the case that always after running alpha, the following more complicated postcondition is true, that says that always after running beta are we safe, which means always after running alpha, semicolon beta are we safe. Whenever it is true that always after running alpha, we get to states where it's true that always after running beta are safe. And of course, this sequential composition axiom much more directly captures how we can decompose reasoning about sequential compositions into subformulas. The subformulas are interesting. Notice these are subformulas that now are all the beta program behaviors are safe. Well, that's clearly a subformula, very easy. But it's also a slightly differently shaped subformula, namely the one that says all of the alpha behaviors such that a different postcondition is true, the one that is all of a sudden talking about extra beta behaviors. But what's still true is that individually, all the formulas here on the right-hand side are easier in the sense that all the hybrid programs have shrunk. So we're still making progress. Good. So what we're exploiting here is the compositional semantics of all the hybrid program operators in order to develop compositional axioms for them in differential dynamic logic. What have we seen? All behaviors of an alpha choice beta program are safe, which means no matter which way alpha choice beta runs, we're safe, means we have to be safe for all alpha behavior. That's this logical formula. And independently, we have to be safe for all beta behavior, which is that logical formula. So the conjunction of those two logical formulas is actually equivalent to the fact that all of the behavior of a system that has a choice to be like alpha or like beta is safe. What a coincidence. I'm so glad the conjunction of two differential dynamic logic formulas is again a differential dynamic logic formula. We've also seen that the sequential composition, alpha semicolon beta, always after running it, are we safe? That means we're always safe after first running alpha then beta, which means over here we need to make sure that all of the beta behavior takes us to safe states. That means over here we need to show that all behaviors of alpha, we need to make sure that afterwards all behaviors of beta are safe, which means this equivalence holds true. The next question we have is the operator of non-deterministic repetition, where again we need to discover an axiom that tells us that all repetitions of alpha a number of times lead us to safe states. That means no matter how often we repeat alpha by running alpha star, alpha, 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 alpha repeatedly, under all of those circumstances do we need to get into safe states where P is true. What do we have to show for that? Well, certainly P had better be true, but that's not enough because we also need to make sure that always after running alpha, is it the system safe? But that's not enough. We also have to make sure that always after running alpha again, we're safe. I guess that means always after running alpha, we need to make sure that always after running alpha, we're safe, and so on and so on and so on and so on. That will unfortunately give us an infinitely large logical formula, which isn't a logical formula. We need to summarize this in a finite way. Do you see how? First of all, we need to show that we're safe right now in the initial state, because otherwise it isn't true that all repetitions of alpha star take us to safe states, because 0 repetitions of alpha star very much is a possibility. But also, always after running alpha, we need to show the same thing again. That means always after running alpha, we need to show that any number of iterations of alpha star do we get into safe states under all of those circumstances, which means in the initial state what we need to show is that we're safe, and after all runs of alpha, all runs of repeating alpha are safe. And that exactly means that always after repeating any number of times alpha are we safe, if and only if we're safe right now. That was for 0 repetitions. And always after running alpha at least once, we're safe again after we repeat alpha any number of times, which overall means we're safe after repeating alpha, if and only if we're safe after 0 rounds and after at least 1 round of repetitions of alpha. Writing down these axioms, of course, is not enough, but we also need to convince ourselves, if we want to use it in our reasoning in the future, once and for all, that the axioms are really correct, which means that they are sound, so all instances in differential Lemma logic of these formulas are really valid formulas, so that we can replace the left-hand side with the right-hand side or vice versa. Let's first understand this for the axiom of non-deterministic choice, which we prove as follows. A transition from an old state omega to a new state nu is possible along a non-deterministic choice of alpha choice beta, if and only if the same transition is possible in either alpha or in beta, just by the very semantics of what the behavior of a non-deterministic choice program is. It's the union of the behaviors of the two. And that means that in the initial state, all behaviors of alpha choice beta are safe, if and only if both all alpha behavior is safe and independently all beta behavior is safe. For the sequential composition axiom, the Soundness proof goes like this. From an old state omega do we get to a new state nu by first running alpha then beta, if and only if for some intermediate state mu can we get from the old state to the intermediate state by running alpha, and from the intermediate state to the new state nu by running beta. And that means the left-hand side formula is true in the state omega if and only if the intermediate state satisfies that all beta behaviors are safe. For all the intermediate states mu we can go to from the old state omega by running alpha, and that is precisely the same as to say that the formula all runs of first alpha then beta are safe is true in the state omega, if and only if in the exact same state omega is the formula true that says after all behavior of alpha is it the case that after all behavior of beta are we safe. And likewise, we can convince ourselves about the soundness of all the other axioms that we've seen for differential Lemma logic. What do we do about diamond modalities? We've seen many axioms for boxes now. Well, what about the poor diamonds? Well, the one thing we could do is, of course, to again zoom in on what exact shape the alpha program has. Is it a sequential composition, a choice, an assignment, an ODE, a test, or a repetition, and develop an equivalence axiom for each of those cases. That will be fine, and it's a good idea to do this on your own. What we will do here is just cover them all in one sweep. How this is going to work is by reminding ourselves about the semantics of the modalities. The alpha diamond modality means that alpha diamond P is true in the state omega whenever there's at least one new state nu that we can go to by running the alpha program to a state where P is true. And if we contrast this with alpha box behavior, then basically it would be very bad news if all of the behavior of alpha is such that every of the states we can go to satisfies not P. Because That's precisely the opposite of there being one that satisfies P. So that means if that's not the case, if it's not the case that all runs of alpha take us to states where not P is true, that means not all of these states are such that the new states we reach satisfies not P, but there's at least one that satisfies P, then that of course precisely means that alpha diamond is true in the initial state. Or overall, there is a way of running alpha to a state where P is true, if and only if it is not the case that all ways of running alpha take us to a state where not P is true. Relate this to the duality that you know from classical quantifiers. There is an x such that P, if and only if it is not the case that for all x's, P is not the case. It's the same principle here as well, just we're not quantifying over real numbers, we're quantifying over the runs of a hybrid program. In other words, the duality axiom relates diamonds to boxes for arbitrary hybrid programs. And because we already know for each shape of hybrid program what its dynamic axiom looks like, we indirectly also know them all for the diamond modalities. Let's investigate what happens when we use these newly developed dynamic axioms for dynamical systems in our familiar bouncing ball example. Here it is. Remember, we only look at the single hop bouncing ball for simplicity. Then our question is of the shape using these abbreviations, that when we start in some initial state where this is true, then all behavior first following a differential equation system, oops, I actually abbreviated that, the second time derivative is minus g for gravity, I should have had another velocity variable. Then the discrete control that's either on the ground or not on the ground, we're safe under all of those circumstances where the safety is defined here. We can reason through using this sequential composition axiom here. Remember, what was it? All runs of first alpha then beta are safe, if and only if after all alpha runs it is the case that all beta runs are safe. We use an instance of that, the one that splits the sequential composition right after the ODE, to say that always after the ODE it is the case that always after running discrete control we're safe. Of course, these are equivalent. That's what we saw previously. Next thing we do is we leave the ODE alone and worry about the phenomenon of the non-deterministic choice right here. For the non-deterministic choice, we have an axiom that says all behaviors of alpha choice beta are safe, if and only if all alpha behavior is safe and independently all beta behavior is safe. Let's use that in this case where we're either on the ground or above ground. Then that's the behavior where we see, first of all, we have to be safe whenever we're on the ground, and we have to be safe whenever we're above ground. Here again, we can zoom in on the sequential composition and use the exact same axiom, just a different instance of it again, that says always after first running alpha, then beta are we safe, if and only if always after running alpha, it is the case that always after running beta we're safe. That means here, always after the test, it needs to be true that always after the assignment we're safe. The tests we can now handle both at the same time using the test axiom. Always after a test are we safe, if and only if test formula implies the safety condition. So here we assume that we're on the ground to proceed with proving the post condition, and here we assume that we're above ground to proceed with proving the post condition. The assignment axiom, the velocity is changing, so we drag and drop it in here. And ultimately, are we left with only dealing with the differential equation, which we solve using the solution axiom. Here's the solution of a differential equation. The position is initial height minus g over 2t squared, and the velocity is changing by minus gravity times time. Again, we have a sequential composition to be worried about. We split that into all behaviors of changing the position, followed by all behaviors of changing the velocity. Remember, in each of those cases, there's exactly only one. Then we use the assignment for the velocity. Velocity occurs here and is replaced by its new value appropriately. Then we use the assignment on the height variable to replace it here, 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 and here, as indicated, and we're left with a formula of actually just real arithmetic. What do we do with the real arithmetic? Well, let's zoom in on the real arithmetic and expand the assumptions formula and the safety condition formula. And then it looks like that if we resolve these assumptions in what's called the premise, so the topmost thing in our proof. This is the formula, which is what we're left with proving, and we need to prove that for all times t. Well, that could be complicated, but let's just zoom in a little moment. Here we see that this assumption is completely identical to just the thing we're trying to prove here flipped, so that should be easy. And over here, what we need to understand is that because gravity is positive, h minus some positive number multiplied a square, which is certainly non-negative. So h minus a non-negative number will certainly be less or equal h itself. So that is easy to see why it's true. On the other case, if this is 0, and of course we're on the ground, then of course 0 is less or equal 0. That is pretty easy. But again, for this reason over here, since gravity is positive, we will also know that h minus some non-negative number is certainly less or equal h. So we've convinced ourselves that a cyber-physical system is really safe. That's super exciting. Okay, admittedly, it was an absolutely grotesquely simplified single-hop bouncing ball. Well, then maybe there's nothing to write home about yet. The point is that in order to convince ourselves this bouncing ball CPS is safe, we developed axioms as general proving techniques that are not specific to bouncing balls. They're for arbitrary hybrid programs alpha, beta, and safety conditions p. They have nothing specific for the bouncing ball, which is precisely the reason why they'll enable us to do similar proofs also for much more complicated CPSs. So let's summarize what we've seen today. Very fundamental axioms of differential dynamic logic. Not all of them, but many super important ones. These axioms are equivalences, so essentially equations of truth. They equate the truth value of two logical formulas with one another. So we know that one side will be true if and only if the other one is true, and since that equivalence was valid, we will be able to use this equivalence in any state that the system could be possibly ever in. We will also be able to use the equivalence in any part of the proof that we're ever in, because, hey, the two are equivalent. For example, all behaviors of a system that has a non-deterministic choice to be like alpha or like beta are safe, if and only if all alpha behaviors are safe and independently all beta behaviors are safe, which is a compositional way of rephrasing this in logic. All behaviors of first running alpha then beta are safe, if and only if after all alpha behavior it is the case that after all beta behavior we're safe. Always after running a differential equation are we safe, if and only if for all times t greater or equal 0, if we plug in the time into the solution y and then change the value of the variable x by a discrete jump to assume the new value that the solution has at time t, then p of x has to be true at all of those, and the two formulas are equivalent if only we make sure that we actually have a solution of this differential equation. And likewise for the other axioms for differential logic, the point is that we have one axiom for each of the hybrid program operators. So using any of those axioms from left to right simplifies the hybrid program structure, which means that even if we start with a terabyte of a hybrid program, if we successively decompose from left to right, we simplify the structure of the hybrid program, which we can only do finally often, even from starting from a terabyte. There's in fact one exception to what I just said. I wonder if you can spot it and find out what we will be doing 2 lectures from now. For the logic connoisseur, there's one aspect of admissibility that I should be warning you about. And that is basically the question I so conveniently talked about p of x and p of e in the assignment axiom, but how exactly are we supposed to read them? Turns out there's an amazingly elegant way of reading them via uniform substitutions, but we'll only get to them in part 4 of the textbook. Until then, we'll make do with a simpler reading. First of all, P of E stands for the same formula that P of X stands for, except all three occurrences of the variable X are replaced by the new term E. Here's a number of examples. What do we have to pay attention to while doing this replacement? Well, first of all, X cannot occur in P of X in places where it's bound by either a quantifier or modality with an assignment or a differential equation for X, because those would then change the value of X, so we're no longer referring to the exact same real number in all of those circumstances. But the same is also true, not just that the variable X cannot be bound by a quantifier or modality, but also no variable in the replacement E can be occurring in a position where it's bound by a quantifier or modality. And all of those circumstances, what we have changed the value that we were referring to. For example, the first equivalence is an instance of the assignment axiom, because what happens is we replace uniformly all occurrences of X with the new value X plus Y. The second example is no instance of the axiom, because over here we're referring to that variable X, whereas X squared is referring to whatever value X was using before the assignment ran, which of course makes this X squared refer to a different value, namely the one that is a function of this one, than it did on the other side. And indeed, for all X squared greater or equal 0, that's the valid formula. But this here is not a valid formula. The next example also is not an instance of the assignment axiom, because even if we left X alone, the Y that we will be plugging into is referring to a different instance, namely for all Y here, than it is out there. Here it is still referring to the previous value of Y. Likewise, in the next example, the variable X plus Y is referring to the value that it had previously, but over here, after replacement, is referring to the value Y got by assigning 5 to it. The next example, even though it looks very complicated, very much is an instance of the axiom, because the value of Y that is referred to here, here, and also here has the value 2 times B, which is not changing throughout the entire hybrid program in post-condition, which is the reason why when the assignment is changing all of the occurrences of Y with 2 times B, they're still referring to the exact same values. In other words, when you're doing the replacements that lead you from the formula P of X to the formula P of E, please pay some attention to logical sanity and make sure you never bind a free variable, because then you go off into logic jail.